This is my SAR ADC. The input voltage is provided using a potentiometer connected between 0 and 5 volts. As the potentiometer is rotated, the voltage sent into the SAR ADC changes continuously. This voltage first enters the LF398 sample and hold amplifier, which captures the voltage at the moment a conversion begins and holds it steady so the value does not change during the conversion process. The circuit can operate in two modes, manual and free running. In manual mode, each conversion is triggered individually using the switch, allowing the process to be observed step by step. In free running mode, the clock continuously drives the SAR logic, so the circuit continuously repeats and converts the input voltage and updates the output automatically. Once a conversion begins, the SAR logic performs a binary search to determine the digital value of the input voltage. Starting with the most significant bit, the circuit temporarily sets a bit and generates the corresponding voltage using the R2R ladder DAC. The comparator then determines whether this trial voltage is higher or lower than the sampled input voltage. Based on this comparison, the circuit either keeps the bit set or clears it before moving on to the next bit. This process repeats until all 7 bits have been evaluated. When the approximation is complete, the final digital value is latched and displayed on the LED outputs. Each LED represents 1 bit of the binary value, allowing the user to visually observe how the circuit translates the analog input voltage into digital representation. The major chips in this project start with the 74HC04. It generates the clock signal that drives the entire SAR conversion process. Next, the 74HC74 provides the flip-flops that form successive approximation registers used to test each bit. Then, the 74HC08 supplies the logic gates used to control the SAR sequencing and bit evaluation. The 74HC273 latches the final digital output and drives the LEDs that display the conversion result. The LF398 samples and holds the input voltage so it remains constant during conversion. The LM393 compares the DAC voltage with the sampled input voltage and determines whether each tested bit should remain set or cleared. In conclusion, this project just demonstrates how analog voltage can be converted into a digital value using successive approximation algorithm, implemented entirely with discrete components. By constructing the clock, SAR logic, DAC comparator, and sample and hold stages individually, the project provides a clear understanding of how many modern ADC systems operate inertially. The completed circuit successfully converts a variable analog input into 7-bit digital output displayed through LEDs, illustrating the relationship between analog signals and digital representation.